Well, hello and welcome to part 3 of my Kaggle project from scratch series. If you haven't seen the previous 2 parts, I recommend watching them before you take a stab at this video. In part 1, I show you how to join a Kaggle competition, get familiar with the data, and to generate questions that I'll want to explore. In part 2, we started to build some graphs using Plotly, and we used them to explore the differences in skills and the tools used across different types of data science related roles. In part 3, we'll expand on this analysis by building a few more graphs and making the code more repeatable. That's something that's really important as you start to build more graphs, you start to analyze more data. We'll also explore the gender differences that are present in the survey. The Kaggle notebooks are both linked below in the description and in the pinned comment, and I recommend following along with those and give them an upvote if you find them helpful. You also might as well throw in a like on the video too while you're at it. Since I'm exploring gender differences, I had my friend Tina Huang, who is a real live woman, double check my analysis for completeness.
Hi!
While she was reviewing it, she gave me a really cool idea. I'm going to leave both of these analyses just a little bit open-ended, and I'll leave it up to you to clone the Kaggle kernels and generate your own findings from the foundation that we've built here. If you're struggling to find a project, a great way to make one is to find someone else's work and just go a few steps past what they've already done. You obviously cite their work, but you can expand past what they've done and call that yours. I've set it all up for you to do just that with this project. Now on to the video. Okay, so let's pick up where we left off last time. So if you recall at the end of the last workbook, I started building an advanced graph and I showed you the 4 iterations that I went through to build that. So the first iteration, I added a simple dropdown with only three options. The second iteration, I added more drop-down menus because we added this loop, and we also added this baseline to compare against the rest of the whole sample. In the third iteration, we added 2 drop-downs that let us compare 2 roles directly to each other. And then in the final background, we added some text here to more clearly show off this graph. So what we're going to do in this portion is we're going to go through and make some additional graphs that don't just show the education level, that show things like IDE of choice, what programming languages people are using, and we can again compare them across roles. So this will be a great way. I'm going to show you how to build all of these kind of self-service tools for you to be able to find the insights. I'll go a little bit into some of the things that I find here, but what's going to be more interesting, hopefully, is my process of how I'm building graphs with some of these different features being represented, and also how I make that into a more consistent method. So rather than me going through and copying and pasting code, can I make a function to do this better? So the first thing that we're going to want to do is I want to go through and experiment with this exact same graph on some programming languages. So what we're going to get is this visual right here. Oops. This visual right here, or we can compare a data scientist versus a data analyst and see what the proportion of programming languages are. So it looks like data analysts use SQL slightly more than data scientists. And we can look at a statistician. They're using R significantly more. So what we're going to do is we're going to take the exact same code, copied and pasted it from our final version of this previous graph, and we're just going to change a couple of things to it. So what we're going to adjust, I think it's important to note, so let's just add a cell here real quick. What's important to note is that this data, so questions Q7, it looks like this. So there's a column for each different entry. In the previous one, I think it was Q5, there was only one entry, one column and a bunch of different entries in it. So we're going to have to format that data a little bit differently. And we'd already done this above. I just copied and pasted code from when we did question 7 in the last part. Essentially, we're going to take all of the columns. So let's just do this. So we're going to take all of these columns and make them into a list, and then we're going to count all of the different columns, reset the index, and then we're going to rename these things language and count, and then we're going to do sort values ascending, and that's going to give us the exact same output as the value counts did from before. So instead of being, well, I guess I can just show you what Q7 looks like, right? So we're going to get this format after running these lines of code compared to that, which is what it was previously. And by doing that, we can just simply replace all of these from the previous one. So instead of having, what was it up here? Instead of having edu and putting this in, we're going to have Q7 languages in there. All right, so we're going to go through, we're going to replace Q7 language here, Q7 count divided by Q7 sum. We're going to go through, and so that's just the first trace. So that's what gives us this blue line. The second trace is what gives us the red line, the initial red line. So let's run this again just for some completeness. So like these initial red lines are what those give us. And then this first one gives us the all samples. So if we go back, all samples, that is why it is the exact same data going in as the trace. Then we have to do one more step. So notice how we created Q7 up here. If we want to filter the data for the specific role, what we're going to have to do is create this little function here. So the function is just going to take all the data, filter it by role, and then it's going to adjust it into that Q7 kind of like value counts format. So we'll just use that whole function and put it in as the Y. And so as you see, it returns the language and then you know, the percent of the population who's using that language. So for the Y value, we're going to want to do this. So we're going to put the 1 there, index, and then for the X value, we're going to put the 0 index. And that's going to produce for all of the, for the drop downs, the filtered data that's going in. So we're able to create that. The only other adjustment that I made, aside from, you know, the traces, those areas, and, you know, the same things down here, was that I added a category array for the language. So all the languages would be lined up in the bottom consistently. As simple as that. So, you know, now we're able to compare programming languages, again, across like a data scientist and let's say a machine learning engineer, or a machine learning engineer and a statistician. So as you can see, the statistician is using a heck of a lot of R compared to a machine learning engineer. Machine learning engineer, I think, is using more than the average population that we're seeing here. Let me make sure that's in the visual. Okay, so yeah, let me just one more time bring up, let's see what a software engineer is using. So a software engineer is using a reasonable amount of Python, definitely not as much as a machine learning engineer. The statistician one is always interesting to me. So statistician's using astronomically more R than a software engineer would be. So the next one I wanted to look at was comparing IDEs. So as you can tell, me going in and replacing all these is a pain in the butt. It's not something we should be doing. It takes forever. There's a lot of stuff that could go wrong. So in a little bit, I'm going to show you how I built this into a function where essentially I just put in the question name and it generates the graph. But in the short term, let's go through this process just one more time with question 9. So instead of question 7, we're going to be creating Q9 here. We're going to add in roles to Q9. I forgot to mention this above. We did this exact same step up here for Q7. That allows us to, again, filter the data. Oops, using that filter function. Sorry, I'm jumping around. Using this filter function here with the roles. If we didn't add roles in here, we wouldn't be able to filter by it in here by the question number. Again, we replace these things here we replace these things here with Q9 instead of Q7. And in this case, we're just adding in question 9 into that function instead of question 7. Pretty straightforward. Again, we just changed this to Q9 language. Obviously, it's not a language, it's an IDE, but I was a little lazy with my naming conventions, so that's what we're getting. And if you can see here, now we can see the IDE of choice. As you guys know, I personally prefer Spider. I'm doing this on Jupyter because, frankly, it's better for visualization. But it's interesting to see how far down on that list it is. Maybe I'm a dinosaur, because I like dinosaurs. But let's compare across like data scientists. So data scientists are using Spider a little less than a little more than the general population. Let's see what a statistician would use. They're obviously using RStudio the most because they primarily use R. Let's look at maybe like a project manager. That's interesting. They use Notepad++. Not surprising. Jupyter is still pretty common with them. So again, this is a fun tool. You can kind of compare these things, think about where you land, and so on. So I think we can learn quite a bit from just these two graphs. For me, starting out here, it seems like a lot of people are really using Python more than anything else, except for statisticians. So if you're looking to become a data analyst, a machine learning engineer, a data scientist, it seems like Python and SQL are consistently the most the most popular there. Which gets into question number 8. So question number 8 asks what programming language people would actually recommend. So let's look here and just kind of explore question number 8 real quickly. And as we can tell, question number, oops, I went the wrong, oh no, did I? Well, it really jumped down there. Okay, question number 8 is just one column with a bunch of rows. So it's going to be very similar again to how we did the cut with the education levels. So I just wanted to have a base case for both styles of questions. So we essentially have either a bunch of different columns with the same values, or we have one column with a bunch of different values. And after we have base cases for both of these, we can make a function that can generalize to both of those things. So just like in the one before, where we were comparing the education level master's degree, PhD, bachelor's degree, we're going to create, instead of edu, edu2, and we're going to fill that into all of these places. We're going from the main data frame here instead of from the questions data frame, because we're only looking at one value and we're doing a value count. So as you can see in these areas, the type of data is almost always the same. And that's something that if I was designing a function correctly, I would just flip out what data goes in here and have all of the structure. Unfortunately, I could not get that to work when I was building it out. It was taking me too much time. So when I actually did the function, I made it far less efficient than that. But a constraint of data science is the time complexity and knowing how much time you should really invest in something. Sometimes it's just not worth it. But yeah, so we're just replacing these things here. Pretty straightforward. Again, I recommend that you look at the code because it'll help you to get an understanding of how all these things work. So let's look at some of the analysis. 80% of the population would recommend Python. I think that that's pretty astounding. Something that's also very interesting, let's look at like statisticians. Even though statisticians use R most commonly, they're still recommending Python. I usually recommend Python to people who are interested in learning data science. That's just something that's one of the things I learned. I actually started dabbling in R before Python, and I'm pretty much a complete Python programmer now. But even software engineers are using a lot of Python, even more than the normal sample. Let's look at a data scientist. So data scientists are just slightly more than the average population, but really interesting to see. So if you're coming in, you're trying to understand, what should I learn to become a data scientist? Python is the number one thing that people are recommending here. So if we're looking at all samples too, R is the second one, but SQL is right behind it. I think SQL is really important especially for landing a job. So the next thing I wanted to look at is just, can we write a function that greatly simplifies how we create these graphs? So instead of, writing all this code over and over again, we can just, do a build graph function, put in what question it is, put in the roles, and add a title, and it'll populate something like this. Let's go through what that looks like. Again, this is not very elegant. I wish I could have done a better job, but I was also tired. So if you want continuation onto this project, something you could do is refactor some of this code, make it more efficient, make it run a little bit better, make it more elegant, and also expand on a lot of the graphs. With this function, we can now create graphs for every question, for every scenario, and we can start comparing and get real insight. This analysis that I'm doing is more of a self-service tool. It's like, hey, you can understand data through some dashboard type things. I would love to see you guys take this a step further and have some markdown language where you're talking about what the findings of these tables are. That's something I would usually do, but again, I thought it would be cool to leave it a little open-ended because I'd love to hear what you guys find with this. So let's get into this function. So the first thing we have is this filter bars that we'd already made a function of before. That's just taking the when we have the data frame like question 7 and there's a column for each answer, we're just filtering it down based on the role and returning that kind of value count format. So you have essentially the indexes are the programming languages and the values are the counts of those, or the counts divided by the sum of those. So like the percentage of the population using it. In this case, we're going to build this graph. We feed in the question number dictionary key value pair. We feed in the roles, and we feed in the title of the graph that we want. So the roles is just that roles data frame that we had. I probably could just feed in the list of roles rather than the list of the list of roles rather than the dictionary of roles. But the data here isn't that big, so I think I can get away with this. But let's get into the meat of this. So if is instance, so if the what we're feeding in is a data frame. So question 7, because it was a bunch of columns, it's read as a data frame. Question 1 or question 5, because it's one column, it's a series. So we're only going to be treating questions with multiple columns for answers using this if statement. So what we're going to do is the exact same thing as creating that Q7 or Q9 like we did up here. Let me go find it. We're going to be running this exact same code to get it into that format where we have whatever values they are, whether it's IDEs, whether it's programming languages in one column, and then the counts in the column next to it. In this case, I changed it from language to feature, and from counts to CNT. We couldn't generalize language, so I didn't think it made sense to do that. We also add the roles column in just like we did before. That is no different. So the next thing we do is we create the figure. We add the first trace, which is just this that we had generated before. It's no different again than Q7 or Q9 that we had in here before to make those previous graphs. We add the exact same thing in here, and we use the same filtered bars in here as well. All of this is virtually the same as those two previous graphs. Again, I would highly reference the code here and look through it and work through it. So all of that is the same. Else is, so if it is a series where it is just one column, we're going to treat it differently and create a graph based on that. So what we're going to do here is we're going to create the same value counts based on feature and roles, and then we're going to add them in to value counts here. I should have been able to not need this and just do something where we would be using just this code, and Q number would be the same as above, and it would flip off based on based on what type of data you're feeding in, but I just couldn't get it to work. So I just made this a lot more robust than it should have. Same thing, we're just replacing this here. We're replacing this here, and we're replacing it in both of the traces. And, with this, in theory, we should be able to generate both types of graphs. So the first graph we build is question 1. So question 1 is a single column. So let's just add another one. So as you can see, that's a single column. And then we'll do question 12, which is the type of hardware by position. And so question 12 is the other kind where it's a data frame. So we can see it's generalized. It works for both use cases. Let's just take a quick second to observe some of this. So let's look at, what is the largest population of data scientists? They're all in that 25 to 34 range. That's the largest group. Maybe compare that to statisticians. We'd expect them to be slightly older, which actually might be the case. Yeah, it's not the case. There's a lot that are way older, but there's some that are younger in that 22 to 24 range, which is really interesting. So again, we can get a lot of really cool insights out of this. For this one, we're building the graph. We're looking at the different types of hardware by position. I thought this would be cool to look at a data scientist versus like a machine learning engineer. So, machine learning engineers are training probably more on the cloud. They're using more advanced tools, more GPUs, whatever that might be. Maybe looking at machine learning engineer compared to data analyst as well. You're seeing data analysts are using a lot less of these to begin with. So hopefully using this function, you can create a lot of self-service dashboards to find some really cool insights and expand on this even further. So that's all I have currently for this part 2 exploratory data analysis related to the different roles. Now we're going to move on to comparing the to see if there's gender differences in this data set. And we're going to switch now. Okay, so let's start talking about the second part of our analysis. It's going to be less exploratory data analysis. Well, technically it's still exploratory data analysis, but we're going to be using some more advanced models. We're going to be using some multiple linear regression, some lasso regression, some random forest, and I'm going to try and get a little bit creative with how we're going to evaluate this problem. So the first thing we're going to do, just like any analysis that I do, is we are going to explore the data. We're going to build a couple of different graphs to hopefully understand first if how the data set is imbalanced based on gender, and then we're also going to look at if we can kind of normalize some of these differences based on the sample proportions. Next, we're going to run a multiple linear regression to understand what contributes most to earning potential. So we're going to look at gender in this frame. We're going to look at years of experience. We're going to look at role and see how some of these things are related. After that, we're going to do a lasso regression, which is a form of regularization. It uses L1 regularization, which means it can effectively remove certain features from the data without us having to consciously do it. It just knows to take them out. After that, I'm going to experiment with some random forest just for a sanity check. Random forest is a nonlinear model, so if we're seeing similar results there, we're probably on the right track. And then I'm going to compare models for subsets that are trained just on female data and just on male data, because I think that'll help us tease out the specific differences in the genders while normalizing for the other factors. So let's continue down this road here. What we're going to do, just pretty normal stuff. We're going to import the data. We're going to trim that first column like we did before. We're going to look at the top of the data just to see what questions there are. We're going to do the exact same thing, chopping up the questions into a dictionary. And this time, instead of roles, we're going to split split it into genders. Something that I wanted to leave in here, which I thought was relevant, is when I got to this point, I stopped and just made essentially a checklist for myself to work through. So I wanted to do a heat map, which I don't think I actually ended up doing. But I did do the brief exploratory data analysis and looked at income across these different things. For me, I really recommend just writing all the steps of what you're going to do down. That keeps you on track. That, I go so many different places. I've mentioned before that my mind can be kind of a dangerous place. So this is a way to keep yourself reined in. So next, we are going to look at the distribution of different genders. So it seems like men are the most common in the survey at almost 80%, women are 19%. Prefer not to say, prefer to self-describe, and non-binary are all relatively low representation in the sample. It's not that they aren't important, but for this use case, I'm just going to compare men and women. It'll just make the visuals a lot cleaner. It'll make it a little bit more simple for our model to understand because of the sparsity of this data. So let's now look at filtering this data frame to just men and women for question 2. And then now let's reevaluate this. So it looks like we're at 80.3% and 19.7% female. So a lot of the things we're doing, we're going to normalize them based on this number. And hopefully we'll be able to see, based on the female population, if this is high or low. So let's first plot the female distribution by role. So, this doesn't really tell us much. Maybe there's more women who are getting master's degrees than bachelor's degrees, and more so than doctoral degrees. But it would help for us to normalize this now. And so we can normalize this by the percent of the female population. So that's what we're going to do in this graph. So we can see that essentially 42% of the women in the sample have master's degrees, 13% have PhDs, and 34%, the highest level of education, is bachelor's degrees. So that's a lot more meaningful. It tells us a better story. We're getting percents here. Again, we can say the same thing for men, but I wanted to take this one step further and normalize based on that 19.7% that we had looked at before. So what we're going to do here is I'll just show you the graph and walk you back through it. So what we can see here is how many more women have master's degrees or less women have bachelor's degrees, ooh, voice crack, than relative to the proportion of the sample, right? So more women than men in the sample actually have proportionally master's degrees and proportionally have doctoral degrees, while significantly, like way less women in the sample proportionally have no formal past education. So what we're going to do is we're just going to take the value counts of the men, the value counts of the women across the different roles. So we're just filtering for men and women, and then the total counts, and then we're taking female degrees divided by the total degrees, and then subtracting that 19% number from it. And then we're coloring it just different things and adding a graph and what have you. So this is an absolute difference. So, the female master's degrees was, must have been close to essentially 20%. And we subtracted 0.197 from it, and we're getting 1% left over. If I did a relative percent, it would be closer to 5%. But for me, that's less interpretable. Doing percents of percents is confusing to me. So I decided not to do that. Next, let's look at female distribution by country. And again, this doesn't really tell us much. It just suggests that, there's a lot of samples from India in general. But I don't know if this female bar proportionally is larger than this female bar for the US. So we'll do the exact same code, copied and pasted, but we switch this out for country instead of role. And let's see instead of education, and let's see what we get there. So we see that Malaysia has proportionally more women. Same with, all of these countries. The United States also proportionally has more women than the average, and so does Canada. The far right of this list is Japan. I think it's probably relevant to just also look at sample sizes. So let's just do so if we look at that, we can see, Japan only, oh, where's Japan? Am I losing my mind? Oh, Japan is a lot. Wow. So I guess just like a very heavily dominated male profession in Japan, which I think is pretty fascinating. Let me just double check that so we can look at female. Yeah, so Japan, 42 of their like 600 are female, which is a lot lower than, for example, U.S. Or India or some of these other countries. Pretty interesting. But yeah. So continuing from there, we can get some pretty like cool insights from that. I mean, there isn't any major takeaways, but what we're gonna do is now be able to create those graphs through a function, just like we did in our previous one, in our previous analysis of the different roles. This is going to be a little easier, though. There's a lot less code than the smorgasbord Frankenstein that I made before. So this will be nice. So we can now just create a norm graph and type in the question number, and this will produce some cool stuff here. So we can see the exact same graph that we had before up here, but with just one line of code from this function that we made. Now let's explore just a couple more things. So first we're going to look at like the amount of, I guess not by country, by role. There we go, fixed, ta-da. So you can see there are a lot more women who are students, who are statisticians, data analysts, currently not employed, research scientists and business analysts, machine learning engineers, data scientists, software engineers. There's less proportional women in the sample. So, I mean, I think that most of these roles are probably higher paying than most of these roles, definitely more so than student and currently not employed. So that's something to think about and something we'd probably want to normalize the data for going forward. Okay, so now let's look at another, I guess, wrinkle in our study here. So if our end goal is to evaluate salary, I think it makes sense to take out non-salary positions like student and currently not employed. And if we do that, we're going to have to reset our baseline. So in this case, if we're removing students and currently not employed, we're going to reduce our baseline to essentially 17.4%. So let's look at a different graph based on that other baseline. So we can look at experience or coding experience, and we can see that a lot more women are on the earlier side of this. A lot more men are on the more experienced side, which many people would expect would be correlated with higher pay. So again, something we have to think about, something we want to normalize for, because that would absolutely skew our results here. The next couple things I built, I'm not the most proud of. Oh no, never mind. This is just the income level, female versus male. Obviously, within the whole sample, women are represented in a lot lower salaries more commonly. This across just data scientists does vary a little bit, but not a good look for the data science community, gender equality in that graph. But we would expect men to be more represented across most salaries, and it's like men are a lot more represented across 2,000 to 3,000, 7,000 to 9,000. There are a lot of there is more female representation across 250,000 to 300,000, but the amount of the sample is really small. So there's only eight of these values here. So that's something again that we need to evaluate and consider. So another thing I wanted to look at just simply is looking at the U.S. So the U.S., the population of female data scientists is higher proportionally, so we would expect a higher proportion across all salary ranges. I mean, again here though, men are dominating the higher salary ranges, so it's beginning to look a lot like there's definitely going to be some immediate gender differences, and I expect the gender differences in pay are still going to be pretty strong even after we normalize for a lot of these factors. So I just wanted to look at some of the sample size here. Obviously, a lot smaller for U.S. population. Next, again, so these are the graphs that I'm not proud of. I just looked at income by role. So let's look at like the highest paying ones here. They're not exactly in order, but we can see that it looks like data scientists carry a lot of the proportion of the highest paid. Maybe that's a CIO, maybe that's something like that, are also represented a lot up there. Research scientists, there are a lot of them that make, I guess, a lot of money here. And then software engineers, if you're a software engineer at Facebook, Amazon, Google, or wherever it is, you can command those types of salaries. I also wanted to look at income by experience. We can do the same thing, zoom in here. As you'd expect, people with 20 plus years of experience have a lot higher salary representation in these higher brackets. And then the last one is related to education. We'll do the same thing here. I do like Plotly for being able to zoom in like this. It's pretty cool. Doctoral degrees, a lot of representation. Master's degrees, a lot of representation in these higher brackets. And then still, bachelor's degrees, a reasonable amount there. So those are other things that are obviously going to have an impact on our salary. So let's start building a model. And if we're building a linear regression that I mentioned before, we can start to figure out almost exactly, assuming that there are linear relationships in these things, almost exactly how much each of these individual factors contributes to how much someone makes. So before I do anything else, though, I really need to build, to convert the data into continuous. So we have salaries and buckets, but that really won't work for our use case. We know that there's order of magnitude differences. They're still technically going to kind of be in buckets, but I think it makes the most sense to convert these into a numeric continuous variable. So what we're going to do is we're going to take, we're going to remove all the nulls from the salary data. And then we're going to clean it up. So there's some dollar signs, there's some commas, there's a greater sign, and we're just going to remove all of those from this data. So now we just have numbers and dashes. Next, we're going to split on that dash, and we're going to take the minimum and maximum and make columns for those. That's pretty straightforward. We're just looking at value counts there. And then after that, we're going to take the average of the minimum and max columns to get the actual dollar values. So as you can see, we have, we still kind of have buckets. There aren't that many possible ones. It's the same as the number of buckets we had. But to us, this is more useful than them being in categorical buckets. So I generally like to use stats models for linear regression. I think that their summary statistics are really good. And if we're looking at understanding and using this as an exploratory analysis, to me, this is going to be more useful at this point in time. So what we're going to do is we're going to take, for our first model, just train it on men and women. And we're going to remove all other gender-related entries. We're going to remove students and currently not employed. And we're also going to remove this column because it's just going to be a pain in the butt. So let's look if there's any null data. Obviously there is, but when we create dummy variables, it will not really matter. So we're going to use pandas get dummies. And what dummy variables are is if you have a categorical, let's say we have the different education levels, master's degree, doctoral, bachelor's. It creates one column for each of those. And that column has a 1 if someone has that degree and a 0 for all other scenarios. So we're creating this sparse matrix. For question 7, part 1, whatever it is, it just fills all the nulls with 0 and keeps 1 for if there's a value there. So as you can see, like question 1, there are buckets for each of the age brackets. For question 2, now there's a man and a woman bucket. And now we can start filling this data in to our model. So the first model we're going to build, we're just going to, the X variable is just going to be this Q2 man column. And so we don't need to put both Q2 man and Q2 women because we removed all the other gender related stuff. If we have, 1 in the man, we know it's a 0 in the other. If we have a 0 in the man, we know it's a 1 in the other. And so that'll be reflected. It'll be redundant if we have both. Next, for stats models, you have to add a constant. That's to get the intercept of the model. It's just a column of all ones. And then we run this model. And this is the part I really like. You have the result summary. I've seen this in R. I used to use SPSS, and you'd see this, and it's great. So we see the R squared is very wimpy. It's 0.06% of the variance is explained by just gender. But we do see that the gender, the gender is significant, and that, it's just gender looking at it, men are expected to make like $13,000 more. So that's pretty meaningful if you ask me. Obviously, this doesn't control for any of those other factors. So let's start adding them in and see if that changes this coefficient or changes anything else in the model. So this line of code, essentially, it allows me to filter the data frame based on the questions I want to include. So let's just run that. So we're going to get questions 2, 4, and 6 for our X data. So we have questions 2, 4, and then, and 5. And so that means we're evaluating it based on education, gender, and role. So we're going to drop Q2 man this time. If we drop Q2 man or we drop Q2 woman, it is the exact same thing. They're just the inverse of each other. We're going to add the constant again. And then we're going to run this model with a little bit more data and see what the summary looks like. So now we're explaining quite a bit more of the data, more of the variance. We're explaining 5% rather than 0.06% of the variance. Being a woman is still, in this case, rather than a man, you saw it was a $10,000 or like a $13,000 pay increase. Being a woman from the sample is like a $12,000, $13,000 decrease. Other things that are relevant, obviously master's degrees, doctoral degrees. Looks like a bachelor degree isn't significant, so I wouldn't put too much weight in this negative coefficient. Being a data analyst is expected to pay less than a data scientist. Software engineer isn't significant, but where's machine learning engineer? I'm losing my mind. Or machine learning engineer, which is not significant either. So interesting findings, interesting coefficients there. Now we're going to add in programming languages. So, let's see if a programming language can impact how much money you make. So, although everyone did recommend Python, I think this is really interesting that if we're looking at programming languages, knowing SQL can bump your pay by almost $9,000 here. And that is a significant relevant variable here. I wouldn't put too much weight in these. We're looking mostly at direction. Because we have so many variables, a lot of them are inevitably correlated. So, our numbers can get a little wonky. But we're still, I think that there's definitely still something here. We're still able to interpret this based on these coefficients. So let's keep going and add in country. So looking at country, we're going to see something pretty fantastic. So the last model we were looking at was at around 8%. Now our R square is up to explaining 35% of the variance based on these variables. So we're getting huge explainability returns from adding in the country of origin. And as you can imagine, Canada, you're looking at, I think it's like a 36,000. I might be off with the decimal place there. I hope not, but pay increase. And the U.S., which is probably at the end, you're looking at, I think it's a $80,000 pay increase. So it's pretty incredible how much impact where you live has on your salary expectations as a data scientist. Honestly, I'd love to do this analysis with just USA data. That would be very interesting to me, but frankly, there just isn't enough data there. I think the largest sample in the survey is from India, so maybe it would be useful to do it with just Indian data and see what that would look like. So the next thing we're going to do is, first we're going to add in, I think, did we add in 20? No, what is 20 again? We're also going to add in question 20, and we'll figure out what that is in a second when I remember. 20 is like the size of the company. But we're also going to run a lasso regression. So a lasso regression is a way to regularize our data. And it, one, helps us prevent, taking outliers into account too much. Two, it helps us work with this sparse data. And three, it allows us to zero some of these coefficients. So when we're using L1 regularization, and we kind of crank our alpha up a little bit, we can start seeing some of these coefficients that aren't as relevant falling out, and it saves us from having to eliminate them by hand. So what we're doing here is we're fitting the model to begin with. We're refitting this model with our, if this is 1, it's L1, and it's a lasso regression. If it's 0, it is a ridge regression. And if it's 0.5, I think that technically makes it an elastic net regression. I could be wrong. If I'm wrong, let me know in the comments. Next, this is the regularization criteria. So the higher this is, the more regularized. If alpha is equal to 0, then it's just a linear regression. Here, I tampered with it to essentially get it to keep the same amount level of R square, but drop out as many variables as possible. And I found that 5 was pretty good for me. Right here, we're just retraining this model with the parameters that we got from the regularized model. I have so much trouble saying that, but regardless, we can see what this summary looks like. So as you can see, our model performs about the same, exactly the same. But if we scroll down here, there are a couple of these features that are now 0. So we're not including these as features in our model, and that helps to reduce multicollinearity. It helps to reduce a whole bunch of issues that we could be having. We have a lot of variables now. We should probably talk about some of the things that we just included. So it looks like some companies, let's see here. So these 3. So smaller companies, 0 to 49 employees, very large companies, and companies that are pretty large, they pay very differently. So the biggest companies are paying the most, and the smallest companies are paying the least. Not exactly surprising. I'm a little surprised, I guess, that maybe a startup, 50 to 249 employees wouldn't be paying more. But I guess if you're looking at straight cash, not options, that isn't that surprising. So the next thing I wanted to do is, because I would say my methods weren't quite as statistically rigorous as they could have been, I wanted to use a random forest regressor to also see if we got similar feature importance results. So a random forest is a nonlinear model. Our lasso regression is technically still a linear model. And if we're comparing the two different models and we're getting similar results, that's probably a good thing. With a random forest regressor, you don't have to worry as much about multicollinearity. Because it is nonlinear, it's just it's splits based. I think it's on entropy. And essentially because of that, you don't have to worry about two variables because it'll always choose. You don't have to worry about two variables being too related because it'll always choose the breaking point that has the most differences. I really didn't explain that well. I'm gonna try and find a resource in the and put it in the description to explain that better. So we're gonna build this random forest classifier with the same x value, and then we're gonna look at the future importances and create a little graph out of it. So interesting thing about random forest is that it is random. So when I do this, we get a little bit different results. So let's make this into 3. Oops. Did I get it right? Man. Okay, that just highlights that graph there. But as you can see, by far the feature that has the most, I guess, importance in the model is if someone's from the US. Next, we're looking at 20 years of experience plus. We have SQL, then the next level experience, size of company, role. R is interesting. That could be a good or a bad thing. Doctoral degree, master's degree. But within this top 25, and there's, I think around 100 features, being a woman is included in that. And so, we are seeing that this is relevant, and that, from our other one, we saw the coefficient for being a woman in this kind of professional domain can hurt your earning potential, which again is sad and is hopefully changing. I won't say that this necessarily eliminates all of the bias through the two approaches that I've done. So I wanted to do one more approach that I thought would normalize for a lot of the other factors. So as we saw, there are a lot more men that have more experience. There are a lot more men that have, not advanced degrees. There are a lot more men that have, the experience is the main thing. There's a lot more men in data scientist and machine learning engineer jobs. So I wanted to try and control for that. And I didn't think that the two methods that I took before would necessarily do that. So what I thought would do that would be if I made two different models, one exclusively using women data and one exclusively using men data. And if we predict the same person with both of these models, hiding what their gender is, if the two genders were perfectly equal in the space, then they'd produce the same predicted salary. If the men's model would always produce more, or the women's model would always produce more, we'd suspect that the mix of things would be an unequal playing field, or that there is inequality there. So let's start with the female model. Oops, I did not define it. We're going to build that with the same data. We're going to get the results in the summary. And one thing we're going to see here is that we got better results for predicting female. It explains a lot more of the variance when we split it out like that. So, that's something to consider when you're building a model in general, is can you break it up? Can composite models work? Is building models for different subsegments of your data going to be more predictive than just building one big omnibus model? This is the final summary of the lasso that we did here. Now let's do the men's model. As you can see, the prediction is a little less accurate here for the men, which I think is pretty interesting. Same thing. But now, when we run the model, for all the data, we're going to just do predict all of the data on the combined data, which is all of the data for the sample. In theory, I should have taken out like a test data set for this. I kind of dropped the ball on that, but it's too late now. It's like pretty late at night, and I want to get this done. So if you did want to expand on this, you could run this on a test set and try to have more explainability for this output than I've created. So what we're going to do here is we're going to add to this combined data the male predictions and the female salary predictions, and then we'll make a little bit of a graph. So we can see here the model for this one person predicted that men would get, the male model predicted $150,000, the female model predicted $65,000. There are some that go the other way. So in this one, the female model predicted $127,000 and the male one predicted $56,000. And some are, pretty close, pretty spot on. I think we'd have a straighter line if it was, or like the slope of the line would probably tell us how equal things are. So let's actually get the slope of the line. So I actually just real quickly ran this regression for female predictions to predict male predictions. This is getting kind of abstract. Maybe it's a thought exercise. But it looks like, if this was 1 and this was 0.9, then and this was also 1, the two models would be the same and equal. And they're not too far off. They're explaining a lot of the same variance, 85%. But, the female model is equal to the male model is equal to the female model times 1.02. So that suggests to us that the male model is predicting consistently a little bit higher, essentially 2% higher values for salary than the female model is. I don't know if that tells us that much more than, like actually comparing the salary. So here we're going to actually add the salary data. And what's this one do? And look at the salaries across a couple different buckets. So although we did make continuous variables, we still kind of have buckets because the continuous variables were almost all the same. So all of the buckets that were, between, I guess, 350 and 500, they all netted out to 400. And we looked at all of the predictions for everyone who was making 400K. And it looks like, so the blue dots are the male model, the red dots are the female model. And it looks like a lot of the time, the male model is predicting on the top part of these portions, even for these, for the lower paying positions. And it looks like a pretty constant trend across the board. There's some a little bit lower here, but it does look like there's a lot of blue on the top there. On the top there. So, something to consider. To me, it looks like there's, comparing the two models, there's definitely some pretty big differences here. Next, we just want to get the differences. So we're taking the male predictions versus the female predictions, and we're looking at the average of those. So on average, the male model is predicting about $10,000 in pay more. And if we're looking at that 2% difference from this regression that we calculated here, that doesn't seem that far off. If we're looking at the standard deviation, it's pretty giant, bigger than this. One thing someone could do is run a t-test. The distribution of the female predictions and the distribution of the male predictions, I think, would be pretty interesting to see if they're significantly different, all evaluating on the same data. As I'd mentioned, I should have done a random sample. That's also somewhere someone else can pick up and improve upon. Let's see here. So I also wanted to look at how often the female model predicted a higher salary than the male model, and it looks like that happens at about a quarter the rate of the male model predicting a higher salary. So I think that this is a really good foundation. I think that there's definitely something there. I barely scratched the surface of this. I've taken a couple different approaches to try and normalize some of the other things. To me, it's pretty apparent that, just starting out with 80% more men in this field, that there's definitely some major gender inequality. I'm hoping that we see a lot of women who are currently students, and hopefully they'll be entering the data science market soon, and we'll start to see a lot more balance in the number of female data scientists, as well as the income inequality, and increasing income equality over time. That's my hope. I also hope that kind of bringing some awareness to these things is helpful in getting that message across, and starting to instigate some change. Again, just like with the last notebook, I would love to see someone kind of expand on the findings here. One thing you can look at is how the model predicted people across different roles, across different countries. You can change around some of the sample sizes. You can make this yours. I would love to see what you come up with. Again, I would love to share this type of stuff with the broader community. So thank you again for watching. I hope you found this useful. I hope you found it informative. And I hope to see you in some of my future videos. So until next time, thank you for watching, and good luck on your data science journey.